So evaluation plays a big role in our learning process. Also, always remember that our methodology is data driven. So naturally, we always start with some data. So as you can see, I have collected some observations. Now, how do I start my learning process? So first of all, we will randomly select few points. There are different ways to do it again. So for the time being, I'm just saying I'm randomly selecting few data points, and then we will hide that from the model. Hide. So why am I doing this? So amongst the entire data, I am hiding few of them. Let's say if I'm taking two, if I have 200 data points, I might hide 10% of it, say 20 of them, right? And the remaining 180 is used to estimate y hat, and the 20 which I have hid from the system, they are used to evaluate the function we have learned. So we are talking about what we call as the train test split. So it's the train test split. So what is hid from the data, the hidden from the model, hidden from model is what we call as test, which is used for evaluation. The rest is used to learn, or so training data is used to estimate. So to estimate this f hat, which best approximates f, we use the training set or the training split, and we use the test set to evaluate test set or the test split. Now, in order to quantify how well a model performs, we define a loss or error function. So previously we have mentioned about this error, right, which is basically the difference between the observed outcome and the predicted outcome. And there are again there is a whole field that basically tells us about what forms a good loss, what is something that is better indicator of what we want to do. But for the timing, let's assume just one of them which I have arbitrarily selected from the set of well established losses. So one way to do this is via the mean squared error or the MSE. And how is the mean squared error calculated? It is calculated as the square of the difference between the true outcome or the observed outcome and the predicted outcome, and we sum it for every n observation. So we mentioned that we had around 200 data points, of which 20 of them were hidden from the system. So here we are talking about around the size of the training data set, which is a 180 of them, size of training set. Now the quantity, the difference is what we typically call as the residual. It measures the error at the ith prediction, where I is from 1 to 180 in our case. So mean square error is by no means the only valid or the best loss function. But what is special about this least squares? So one thing is that it has a nice probabilistic interpretation, which makes it easy to compute. Many times we use what we call as the root mean squared error, which is nothing but the square root of the function or the expression we have discussed previously. So it's like the root of the residual summed and averaged. So we choose this loss in order to minimize the predictive errors made by our model, that is to minimize our loss function. So we use MSE as our loss function, which we have mentioned as the true or the observed outcome in the training set and the predicted outcome. Now, how do we get the predicted outcome? So please remember, y hat I is nothing but it is the function f hat xi, right? And we know what is f hat. F hat is nothing but beta 1x plus beta 0. So please do understand that, so beta 1 xi, the beta 1 and beta 0 are going to be the same irrespective of the number of observations. Like what I mean was, we are going to have a common beta 1 and beta 0, which we call as the coefficients, and they are being learned and they are going to be common for all the xi's, all the observations, right? So we replace the y hat with its expression, and then the optimal value that we are looking here, right? The optimal value for beta 0 hat and beta 1 hat, so it should be the argmin of beta 0 beta 1 of the loss which has beta 0 beta 1. And how do we compute it? It's quite simple. We compute the residuals and then calculate the loss function for every possible beta 0 and beta 1. So what we are talking about here is basically an exhaustive search or an exhaustively enumerating all possible beta 0 beta 1 combinations. And if we do that, let's assume we do that, we just have to see which one gave us the minimum loss, and then it makes it that basically tells us the function, right, which is the f hat. Now the question is that this sounds, or when we say it, it may probably is easy, but how do we do that? How can we exhaustively search for all possible approaches? Doesn't it sound too much of work basically? So don't worry, we have a better alternative, which is to take the partial derivatives, the partial derivatives of L, the loss, with respect to beta 0, with respect to beta 0 and beta 1, right, set to 0 and find the minimum. This procedure will give us the explicit formula for beta 0 and beta 1, and this is how we can achieve this. Now there are multiple ways to measure the fitness of the model. In fact, there are multiple ways or multiple loss functions. There can be a maximum absolute deviation, sum of absolute deviations, and sum of squared errors. Now the question is that there are more, I'm just stating 3. So let's now look at a possible scenario. in what scenarios would you choose mean absolute deviation or max absolute deviation? So you can say that there is this max absolute deviation which is in the middle, there is this orange which is the mean absolute deviation, right? So what do you think can be better, like we can use this instead of the MSC we have used? What scenarios? So by looking at this, what I can suggest here would be that if you think of, say, something like a credit data with credit, then if you want to eliminate outliers, I would suggest this max absolute deviation can be a good suggestion. The mean absolute deviation can be a good option when you're looking for problems where we are looking for profit and opportunity cost. What is a real world scenario? Probably real estate. So let's say credit data for the max and real estate for the mean. So now we, if you're looking at evaluating the significance of predictors, we interpret the term in our observation, which is y is equal to fx plus e epsilon, to be noise introduced by random variations in natural systems or imprecisions of our scientific instruments. So it's basically the standard error. If we knew the exact form of, say, f, for example, then there was no need for this epsilon. So if we knew the exact form of f, where f of x is nothing but, we can say, beta 0 plus beta 1x, then there was no need for estimating epsilons, as the betas would have been exact.